yeah, so yesterday we talked about transformations, we talked about translation, we talked about, what are the other two we talked about? Translation, reflection, and rotation. Today we're going to focus just on translation. Okay? So we're going to break it down a little bit more. Is that okay? Translation. A translation is a rigid motion. We discussed that yesterday briefly, right? Rigid motion that slides every point on a figure the same in the same direction. Okay, so every point on that figure is sliding the same way and in the same direction. Okay, can't have any outliers just messing us up. Okay, and so the reason I had you take out your computers is because we're going to play around with it a little bit. Okay, because there's things you can do. I believe there's different settings, like you can select things, you can draw things, you can change the shape, the color, you can delete it and start over, yes, okay? And so this is what we're going to do. When we want to refer to points on the original figure, okay? I drew two images on this graph board over here. One is a translated version and one is the original image. I'm going to tell you how to decipher them. Okay. Over here, I have this parallelogram that is ABC or ABDC. Okay, ABDC. I know that this was the original image. Can anyone tell me why I know that's the original image? Anyone got a guess? What?
The dash marks.
The dash marks. These little hash marks up here. Okay, that means something called mapped. Okay, it stands for mapped. It means that I mapped this point from that original point. I mapped it. I translated it. So when you map something, you're translating it. You're using some type of transformation. Translation, rotation, reflection. But that little tick mark tells me that I mapped it. So it's the new one. Here's something that's going to blow your mind. I could pretend that this is perfect. I could redraw D, C, B, A. I could redraw those again. Okay? And if I have two tick marks, that means that it's been double mapped. Okay, so pretend that's perfect, like the same length of the other one. So I could say original image, mapped image, double mapped image. You can do more than one thing to it. Okay? Sometimes it's going to break it down for you because sometimes we do a translation and then we do a rotation. Okay? And sometimes it's just going to show you the final thing. Like, oh, it's from here mapped to here, and you got to figure out what the two steps were. Sometimes it's going to break it down for you. But you can map something as many times as you want. You just keep adding tick marks. Okay? Make sense? We're not going to do much with that today. But okay, look at your little gnome. You see your little gnome on your page? Okay? I want you to play around with that for a little bit. Plug in some numbers for the left and right. Plug some numbers in for up and down. I would put mine on the screen, but my thing is recording. And then press move when you do that. Just plug in some numbers and let's move it.
He's off the screen.
Carly moved hers off the screen.
I think he moved off the screen.
They moved off the screen because you put in too large of numbers. Start with some things under 5. Let's go there. How's that?
Darn it.
Okay. Let's see what it looks like when we move him like 5 or something. So do you see how it moves him? If you put left and right as different numbers, you see how it moves it to the left and then translates it from there? It has a double mapped image. By the time it finishes to that last one, it's been double mapped. Okay, you see your little gnome figure? I believe you can change it also if you go to, let me play with yours, Carlin. Okay, go to shape and do me a favor. Pick the one that looks, that's the fourth, well, yeah, the fourth one down. It's like a, oh wait, here. Okay, maybe. Oh, shoot, what did I do? Oh, I get to draw it on. Well, I'm hitting on the draw characteristic for some reason. What did I do, Carly? I don't know.
You're messing up my graph.
destroyed your graph. I'm so sorry. But it's like paused. Do you see how it's frozen and I don't know what happened? Hey, Carly's gonna pretend that I didn't mess up her graph. Can you guys delete that graph? Is it deletable? That's my question. Okay, it doesn't let you press the trash can? Okay, that's all I need to know. Okay.
Oh, I refreshed it and just went back to it.
Oh, okay. Let's see this. In the activity, you can draw an experiment with translating a figure by adjusting its x and y coordinates. Try switching it to, try switching the shape. Let's see if you can switch your shape first. Can you switch your shape? Or just lets you draw it?
Doesn't change.
Okay, I'll have to play it. I'll play around with that later and figure out what's going on with that. You're drawing. You're on the draw. Press select. Press the arrow that says select. Now press the shape that you want. I don't know. Hit the graph. Nope.
Yeah, you can drag it.
Oh, you can drag the shape over. Okay. Caden's smarter than us. So press select.
Oh my
Bruh.
You're gonna press select. You're gonna go to the shape. I want you to pick the fourth one down. Slide it. You have to slide it over, Carly. So press this and hit that. Now slide it over.
No, like,
Slide it over.
like click this shape and then just drag on the screen.
There you go. So that you get
Just
this.
click select.
Now
No,
This is terrible.
she's struggling. Okay. Anyhow, we'll figure it out later. So you can play with that, okay, and figure out some of this stuff. Now let's talk about the math behind this. Okay. When you're doing a translation, okay, this says EF is translated 3 units down and 5 units to the right. What is its new location? Let me give you what EF started at. Let's say that EF starts at, I don't know, let me think about this. Let's say EF starts at 10, -7, okay? 10, -7 is EF. And they want to know if it is translated 3 units down and 5 units to the right, what is its new location? What do you think I do to that? What would I do to 10, -7 to get my new translation? Okay, but I can do that without graphing it. What? Good. Yes. So because I know it goes down, I know that's my x-axis. Yes. No, it's my y-axis. So when it goes down, it's my y-axis. Up or down is y. So this tells me that's my y-axis. Left and right tells me it's my x-axis. So what I'm doing is I'm adding 3 to -7, correct? But I'm adding 3 down. So if I'm going 3 down, is it +3 or -3? -3, okay? So I'm going to have this, 10 plus something, and I'm going to have -7 plus -3. What goes here? If it's going to the right 5 units, is it plus or minus? Plus. So my new translated point is 15, -10. Do you see how that works mathematically? So when you're translating something, you're just adding and subtracting to the x and y. So if they want you to do it algebraically, that's how you do it algebraically. Does that make sense? Are we okay with that? Do any of you guys play chess
Yeah,
or checkers?
Yeah.
Me? Okay. In checkers, you're sliding, right? You're translating your checkers all the time because they can only slide diagonally. They can slide this space up, that space, whatever. You get what I'm saying? Okay. So things happen. That's how we do translations, like in a real world situation. You can translate your pieces. Okay. A transformation that creates a congruent figure. We might have talked about this yesterday. A transformation that completes a congruent figure or that makes a congruent figure is called an isometry. Have you heard of that before? Isometry? So it is a translation that creates a congruent figure. Translation that creates a congruent figure is an isometry. I cannot talk today. I'm so sorry. Okay. So when we are doing these, when they show those mapped marks, those are isometries to the original image. Okay? So things that we talked about. So on your homework tonight, they might give you something like this, where they give you a picture of A, B, D, C. And they say, translate this 2 units to the right, 7 units down. And you're going to take each of these points and add 2 units to the right to it, 7 units down. 2 units to the right, 7 units. And you're going to show me the math behind all those points. Can you handle it? Adding and subtracting. We got that? Okay? So that's what we're starting with today. Okay. Then they kind of introduce us, if you look at page 59 in your textbook, they kind of introduce us to something called a proof, which we're going to get really introduced to in a couple of chapters. Okay? But there are different ways you can do proofs, and so I kind of want to look over this way real quick. So turn to 59 for me. Okay? So proof is you basically describing what you did using the rules of geometry to solve from where you started to where you went. Okay? So you're saying there's a T-chart proof where I list all my items and I say step 1, and then I say this is why I can do step 1. Step 2, this is why I can do step 2. That's how I think. I like order. Okay? There's something called a paragraph proof. And people, especially like people that are artsy or people that enjoy English, this is a lot of times easier for people to write. Okay? Paragraph proof is like what it says. It's a paragraph that proves what you did. Okay? If you're not a wordy person, you don't like these ones. No one wants to write a paragraph, that's me. I'm not that person. Okay? So this paragraph proof on page 59, okay, it says this translation creates a congruent triangle, and it is an isometry for triangles. Determine if translation is isometry for all figures and explain your reasoning. Okay? And it says they use a format called a paragraph proof to prove this. The paragraph proof states this. And watch all the detail that goes into this. Before we translate the figure, we construct auxiliary segments so that each interior angle of the figure is part of a triangle. So you see on that diagram how they broke it down so that each angle is broken into triangles. So that there's a pentagon sitting inside of that object. Okay. Then we translate the figure and its auxiliary segments. From our work above, we know that a figure's side and the auxiliary segments will be congruent to its image's side and auxiliary segments. Because a translation is an isometry for triangles, each triangle inside the figure is congruent to the corresponding triangle in the image. This means that each interior angle of the figure is congruent to the corresponding angles of the image. All angles and sides of this figure are congruent to those in the image, so translation is an isometry for all figures. We have proved that translation preserves congruency for all figures. So what they did is they used their knowledge that triangles have isometry, broke the object that they had down into triangles that were congruent to the original triangles, and then said because all of these little triangles are congruent to each other, the overall shape is congruent to each other. Does that make sense? Okay? So it's a lot of words. You get what I'm saying there? That's why I'm a step person. I don't do those words. I'm like, that's a bunch of stuff I didn't need. Okay? But that is what this section is about. We're just focusing on translations. You might need to use your GNOME tonight to do some of this. Double check your work with your GNOME. Plug the coordinates in, moving up, left, or right, left, or whatever. Plug your coordinates in, they tell you. And check where that GNOME moves to make sure that you did your math right. It's a good way to check. Okay?